a look at classification models and convolutional neural networks today, but we're actually going to start with a quick little coding example with the handwritten data digit recognition. So if you want to go ahead and create a blank Colab notebook, we'll start with a brief little coding example, and then we will hop right into it. And yeah, we'll go ahead and get started. If Shreyas joins us, I can get him up to speed in a second. All right. And for this example, we actually don't need any data sets. Well, we do, it's just that it's preloaded onto it. So if you remember yesterday, I was talking about the handwritten data or handwritten digit recognition, right? So if a person draws a number on, well, like a piece of paper or something, we want to train a neural network to automatically convert that number into actual text, right? So it's not, a person can't draw a perfect number, yet we want the neural network to be able to pick up on this and automatically recognize what type of digit it is. So now let's go and cover some of our fundamentals again. I think this will be helpful for everyone, but also for Palash, who's joining us today. So let's start with I guess we'll take a step into looking at our deep neural network, right? So our deep neural network, it has our input layer. It has all of these hidden layers with all of the neurons in between, and then it has an output layer. So if we're working with single digit numbers, right? If we're just working with anything that's not double digit, I guess let's start with the input layer. Actually, I'm going to let's pull up the data set and take a look at it. So again, what I was talking about yesterday, this is the hello world of machine learning and AI. And it's just everyone's first example is the MNIST database of handwritten digits. Everyone's first project is to work with this, and I'm really glad to be doing this together with you guys. I think it's a great example and very applicable. All right, so let's take a look at what this data set is talking about. And Shreyas, you didn't miss anything. We just got started, and we're going to start with the handwritten digit data set. So it says the MNIST database has a training set of 60,000 examples and a test set of 10,000 examples, right? So remember how we talked about all of our data is split into train, test, and validation, or in our case, we're just splitting it into train and test, right? So we already have a train test split built into the model. So that's why this is the hello world of ML, right? Because they already do some of the splitting for us, which is very, very nice. These digits have also been size normalized. So what did I say was one of the criteria of putting images into a model? Why does, what does that mean?
They all have to have the same dimensions and pixels.
Yeah, exactly. So they all have to have the same pixel dimensions. And usually for the sake of ease, we usually fit in square images into our CNN, like it's the same length by the same width. And that just makes it, I guess, standardized for the model, right? We have to fit in the same size, but we also like to feed in square images into convolutional neural networks. So it's great that you remember that. We barely touched on it last time. And then last but not least, it says it's centered around a fixed sized image, right? So that's also very helpful because when we have, like, let's say we just have a 6, it's better to have it right smack in the center of the image than on like the top left, right? It's just, I don't know, it just makes it easier for the computer to take a look at. All right, so the MNIST data set. So there are two things that make it very easy. The first thing is that the images are only black and white, so we don't have to deal with RGB image data. If you remember lesson 8 of Python for Research, right? An image is made up of those 3 channels, R, G, and B. However, the MNIST dataset just has one channel, right? It's just a grayscale channel going from 0 being black to 255 being white. And it's just either black or white, right? It's almost like a thresholded image, right? When we took that picture of the Legos and we just turned it into black and white. It's already been done for us. So a great starting example again. And second, it's 28 by 28. So it's a super small image, right? 28 by 28 pixel image is extremely small. If you've ever hovered over images on like Google Images, right? They usually have like 100 by 100 pixels, or like even thousands by thousands pixels. So 28 by 28 is super small. So that also allows us to focus on the I guess on the image data and which of these 28 by 28 pixels are basically how do you put it, are important to determining the type of number that it is, right? So now let's take a look back at our slides. So we talked about the first layer. So remember how in the first layer, when we had 19 features in our tabular data, our first layer had 19 of these neurons, right? 19 of this first layer had 19 neurons in it. So now, knowing that we have an image and we know its dimensions, does anyone have any ideas as to how many neurons we would have in the first layer? This is a tricky question to think about, right? Because it can't be 28 because we have a length and a width. So let me open this chat. You're kind of confused. Yeah, sure. What can I
Can you
clarify?
say the question again?
Yeah, how many neurons should we have in the first input layer of our neural network? Any thoughts? If we know that our data set is only 28 by 28 images.
Would it be 2? It's only black and white.
Not quite. It's not looking at the color. The color it'll look at by itself. That is a good guess. Yeah, if you're blanking, that's no worries. It's actually not too complicated of an answer. But think about what is an image again? What is an image?
A series of pixels.
A series of pixels, right?
Of pixels.
Yeah, so how many pixels are in our image? In every single one of these MNIST handwritten database
28?
images? Not just 28.
Whatever 28 times 28 is.
Yeah, 28 times 28. Yeah, that's the right answer, right? It's a square. It's 784. 784. So we have 784 pixels in every single one of these images. Let's look at an example of. And Shri, does that kind of make sense why we have 784 features in the first layer? It's because each pixel is a feature. So we have to do 28 times 28 because that's the size of the pixel or size of the length and the width. So this is what the data set looks like. Yeah, feel free to look it up on your own computer as well if you want to take a look at it. But here's what the data set looks like. And we want to train a neural network to recognize these numbers. So pretty insane, right? Because if we look at this, right, some people drew a 1 at like a 45-degree angle for whatever reason. Some people 7s have those little lines in between them, but some of them don't. This 8 simply looks like a blob. It looks like someone used, like a thick Sharpie to draw it, and they just didn't leave any space or something in between it. So we have all sorts of stuff here, right? No 2 looks the same. None of these numbers look the same as each other, even in the same classification. So it'll be impressive if our model is able to detect this with a high accuracy, right? It'll be pretty impressive. Let's go ahead and hop into the code. So luckily the code isn't very long. And we won't be needing any convolutional neural networks. We can simply use a simple categorical neural network for this issue and achieve a reasonable accuracy. So let's import all of our data sets, pandas as PD, and we'll learn about what convolutional neural networks are right after we finish this example, simply because it builds on this knowledge. Import MNIST. So remember I talked about how Keras is the library that we use for deep learning, right? It's built on top of TensorFlow. Yesterday when I imported it, I did tensorflow.keras.datasets. I think it's the same thing, so that's why I actually just took it out for today's lesson. I think you can just do keras.datasets. Import MNIST. I forgot what it stands for, to be honest. What does it stand for? What does MNIST?
Wait, that line from keras.datasets import MNIST, is that we're importing our photo dataset?
Yeah, that's importing our photo data set of all the images. Modified National Institute of Standards and Technology database. Okay. Yeah, whatever. That's pretty irrelevant. But yeah, this is going to be our data set. And then what type of model are we building? Do you remember when what was the type of model where one layer comes after the other? Any ideas? Remember how we did model.add and model.add? We kept doing that for every single one of our dense layers. But at the very beginning, we had to specify what type of model it is that allows us to just keep adding layers.
Linear regression model?
Not quite a linear regression model. Yesterday, we used a neural network to perform linear regression. That's a good, I guess that was not the best question, but it was just like a sequential model, right? Where it's a sequence of layers, right? One after the other. Shri said artificial neural network. Yeah, that's what we will be creating. Yeah, I guess that is also the type of model. So yeah, your answer is not wrong. Your answer is not wrong. So from keras.models, import sequential. Sequential simply meaning that every layer in our neural network will be connected to the following layer, and we can just add layers one after the other, right? And then what was the layer called where every input is connected to every output of the next layer?
Dense.
Yeah, dense layer. So let's go ahead and do from keras.layers, import dense. And for Palash, I'll quickly explain what dense means. Dense means that if you see this diagram over here, one of these neurons, and these neurons are represented by a circle, one of these neurons is connected to every single one of the neurons in the following layer, like to its right. So if you imagine going from left to right, every single one of the previous neurons is densely connected, or it's like webbed together with every single one of the neurons in the following layer, if that makes sense. So it's basically passing some information from the previous layer to the next layer, to every part of the next layer. I should be more clear about that. From keras.utils import to categorical. So what to categorical does is it one-hot encodes our labels for us. So it's very useful simply because it avoids a lot of the manual hassle of one-hot encoding things. You simply you call to categorical and it just does it all for you. It's very nice. So yeah, let's go ahead. That's all of our import statements. And I'll quickly, actually, I do want to explain one-hot encoding again because there was a lot of confusion about what it means. So, and actually, I'll actually apply it to the example we're working with today, right? So how many possible, so in our output layer, how many neurons are we going to have in our output layer? Just taking a look at this data.
Outputs, not 10.
Yes, 10, perfect, yeah. Because we have the final classification can either be a 0, a 1, a 2, 3, 4, 5, 6, 7, 8, 9, right? So there are 10 possibilities. We're not dealing with double digits or anything, just single digits here. And yeah, great that you remembered that. So our output layer has to match the number of possibilities in our data set, right? So hence we have 10 possible outputs in our final layer. And we can kind of explore this using one-hot encoding. So I guess, does someone want to, I guess, try and explain how would this table be modified to better suit one-hot encoding for the MNIST database? What would that look like? Any thoughts? How would this change from just color red, color blue, color green to one-hot encoding? What would we put on this blue column?
Black, white.
It's not the color because we're not
No.
trying to detect whether the image is black or white, right?
We're replacing the color red, blue, and green with
Oh, it's the
0 through
numbers.
9.
Yeah,
Yeah,
0
with the
through 9.
numbers.
Yeah, exactly. What'd you ask, Shri?
No, I was just saying you'd probably replace them with the numbers.
Yeah, you would replace them with the numbers 0 through 9. So instead of red, blue, green, we would have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And the way that we would one hot encode it is that if it's a 1, we put a little check mark or a 1 inside of the 1 box, and so on and so forth for all of the types. So for Palash that missed it yesterday, basically one hot encoding allows us to represent our labels in either zeros or ones. So if you look at this here, where we have the first data point is red, the second one is blue, then green, then back to blue. All we do is, you can imagine it like putting a little check mark inside of a box and an X, check mark being a 1 and X being a 0. So simply we put a little check mark inside of red when the data point is red, right? And then we put a 0 or an X everywhere else. So that way we can represent categorical data, right? Something that could be plotted on like a bar chart or something, simply using ones and zeros, if that makes sense.
Yeah, that makes sense.
All right, cool. And two categorical, which we did not cover yesterday. This is the way that we do that in code, by the way. All right, so let's go ahead and remember how I said that the researcher was kind enough to already sort it into X train, Y train, and X test and Y test for us. X test and Y test. And this is equal to mnist.load data. So a lot of the inbuilt data sets that are actually they're like built into Keras. We actually don't need to download them from the internet or anything. I think there's one for like dog, cat, like airplane images. It's called CFAR10. I'm actually thinking about using that as the example tomorrow. I think tomorrow we'll code a malaria classifier and we'll code an image classifier just back to back. And today we'll talk about CNNs, which is tough. And we'll apply that stuff tomorrow. But yeah, here's the mnist.load data set. And go ahead and run that, and it'll actually pull it from a Google API. It should be pretty fast. It's basically stored online, and it just grabs it for us, basically, very quickly.
Here, so I'm sorry, it's a little bit late, but what exactly is the two categorical again?
That's how we will one-hot encode our labels. So basically, let's say we have our training data, right? Or not our training. So our training data is the image, right? Because that's what we're going to be training on. What is stored inside of Y?
What's our test data?
Not quite.
No, the answer.
Yeah, the answer, right? Or the labels, right? So Y-train should be a array that looks something like this, right? It's just a bunch of labels that correspond with the X-train image. So let's say the first image inside of our X-train is a 1. So the first label inside of Y-train is a 1, right? It would look something like this, just digits from 0 to 9, right? And they would just be in the order that the X-train is in. So what two categorical will do? Let's actually one-hot encode this for us. Any ideas on what the first one-hot encoding would look like for this data set? Let's actually shorten this down into just 3 examples, and let's do all 3 of them. What is the first one-hot encoding going to look like? For, let's say this was our Y-train data set, and if we were to one-hot encode this, what would it look like?
1 0 0 1 1 0 0 0.
It's actually 3 separate arrays, because if you were to do it like that, right, it would get confusing. It would think that there's a 1, a 4, and a 5. So we would have to do it in 3 separate arrays, as so. Any ideas now? You were on the right track. And also remember that 0 is the first number in the data set. So
0 is part of the data set? Okay,
yeah, 0 is part of the data set.
0, 1, and then all the rest is zeros?
Yeah, 0, 1, right? And then we're going to have 0 for 2, 0 for 3, 0 for 4, 0 for 5, 0 for 6, 0 for 7, 0 for 8, and 0 for 9, right? So this is how the 1 looks like when it's one-hot encoded, right? So let's just go ahead and copy this actually and paste this here, paste this here. So now what would these following two be? What would this one be? Someone else answer other than Treos.
It would be the fifth one would be 1.
Yeah, so this is 0, 1, 2, 3, 4, and since it's a 4, we would replace this with a 1, right? And that's what represents this 4 over here. And then the next one is easy enough because it comes 1 after. So this is what one-hot encoding basically looks like. And 2 categorical, you simply do you simply do 2 categorical on this, and it'll one-hot encode it for you. I think it'll actually just run like this. So let's do encoded equals one-hot encode or 2 categorical, right? And let's just print out encoded and see what returns. And lo and behold, here we have it. And the reason it looks like this is because it doesn't know that the data goes from 0 to 9, right? So it just stopped at 5 because that was the maximum value that we passed in. Does that make sense? How one-hot encoded it? Yes, no, we're good? All right. I'll take that as a yes, but yes. So hopefully one-hot encoding makes sense. 2 categorical just does a lot of this brutal like manual labeling for us, right? Very, very simple. And I feel confident you could actually program a custom 2 categorical example on your own if you wanted to. You could. I don't think it'll be that hard. All right, so let's go ahead and create our sequential model. Model equals sequential, right? That's always the first step of creating any neural network architecture when it's adding one layer after the other. Then what we will do is do model.add. So now quick sanity check. What is the size of this first dense layer? Or what is the input of this first dense layer? Remember, think back to the images that we're passing in. How large is that data? Shreyas, you're muted if you were speaking.
Yeah, I just realized that. Is it 720? Is it the number of pixels or is it 10, like the number of numbers that were in?
Yeah, it's the number of pixels because the number 10 is going to be our output because it can be 10 possible things. So that's at the end. So yeah, it's 784, and like you don't have to do that math in your head or on a calculator. Just simply do it in a new cell right here, and yeah, it'll show you 784. Great. Let's go ahead and copy that in. And let's go ahead and pass in our activation functions. Remember, we use the rectified linear unit activation all the way up until the last layer. And then what type of activation do we use for the last layer? Does anyone remember?
Sigmoid?
Yeah, sigmoid. And sigmoid was for binary. Does anyone remember the multi-class classification alternative to sigmoid? We barely covered it, so it's okay if you don't remember it. When you have more than 2 classes, you have to use something that performs sigmoid on every class, so it's not called sigmoid anymore. It starts with an S as well.
Softmax?
Yeah, softmax. Awesome. Very good. And then when we're using image data, we also have to pass in something called input shape. What do you think the argument for input shape is? Any ideas? It's just 28 by 28, just the size of the image. 28 times 28. And we put a comma after this too. It's called a trailing comma to specify that like don't worry about the color channels, right? Because sometimes you have 3 color channels. So we'll just put that trailing comma there to make it work. All right. So once you have this down, we can actually just go ahead and add the exact same dense layer. Let's go ahead and just have one hidden layer in this. So we'll just have one of these. And now let's move on to our output layer. All right, our output layer. So our output layer is going to be even simpler than the previous 2 steps. We'll add another dense layer, and now this time Shreyas, what is in our output layer? And
10.
Noah answered this. What?
10.
Yeah, 10. Perfect. Because we have 10 possible numbers, and we know that we're gonna have activation equals softmax. Perfect.
So
Okay.
where would you put like the dense layer would be like 1, or is that like conditional?
The dense layer is 1 if you only have a binary classification. So like dogs versus cats, or if you're
Oh,
trying to
okay.
determine one number. Like remember in regression, like we're not trying to determine like multiple house prices, right? It's just one house price based on all of the data. So you would simply do dense 1, right? Because there's only one price that could possibly come out from the model for every single data point, if that makes sense. But in the last couple of things that we're doing, actually, when we're detecting malaria, right, we're going to do either malaria or not malaria. So you would have dense of 1, right, because it can only be 2 possible things. It can either be an uninfected cell or an infected red blood cell, right? So only 2 possible things, and hence it would be dense 1. But whenever we have categorical data, which is more than 1, we would just specify the number of possibilities it could be. So does that make sense, Sri?
Yeah.
Okay, cool. So remember our last step in our model is to compile the model. What was the optimizer that I said to just kind of use for this class and for your projects in general? Oops,
Atom.
yeah, the Atom optimizer. And then, so you remember how we did loss equals mean squared error yesterday? So that was a loss that we're familiar with. However, the 2 types of loss that we will be using is called categorical cross entropy. I'm not going to go into the math behind that because it involves a lot of calculus. So we will not go over what that is. But simply, there's a very easy thing to remember: categorical cross entropy for more than 2 classes. And we would simply just use, we would simply pass in binary cross entropy for 2 classes. So whenever you're working on your own project, just keep this in mind. Whenever you have more than 2 classes, it's categorical, and whenever you have 2 classes, it's just binary cross entropy. And cross entropy, you can just imagine it like it's just an error metric that simply we want to get that J curve, right, where the longer we train, the lower this categorical cross entropy loss is. We want to minimize it. And then what was another metric that we talked about yesterday towards the end that I said wasn't a great metric when we had unbalanced classes? Very standard. Does anyone? Yeah, accuracy, right? So accuracy is simply like your grade on a test, right? If you get 95 questions right out of a 100-question test, you get a 95% score on it. And the MNIST data set is a very well-balanced data set, and hence we can use accuracy, and it should give us a very good idea of what we're getting at. All right?
Wait, so binary cross entropy. So that's, what do you mean by 2 classes? I'm confused by that.
Like we'll be using, if you were to create a cat versus dog classifier, you would use binary cross entropy because there's only 2 possibilities. So I think binary cross entropy basically works with like the sigmoid function, and categorical works with the softmax function.
So like there'll be only 2 possible results.
Yeah, there'll only be 2 possible results, right? It could either be a cat or a dog, and there's nothing else it could possibly be for the model, at least, or as far as the model is concerned.
And so wait, so for categorical cross entropy, you can only use softmax?
Yeah, because we use softmax when we're dealing with more than 2 classes, right? So naturally they fit together.
Okay, and then sigmoid is only for 2 classes.
Yes, sigmoid is only for 2 classes. Let's actually make a little bit of a note about that. Softmax and categorical cross entropy for more than 2 classes, and sigmoid and binary cross entropy for 2 classes. So these are your 2 possibilities. Yeah, I think actually if you aren't writing down anything, this is something I would at least write down in your notebook or just make a sticky note or something. I think this is crucial. People forget all the time and then they wonder why their code is like so strange, because trust me, the code will do very weird things if you accidentally put the wrong one. It is really bizarre. I've seen it firsthand. It is very strange. Let's
Will
go
we
ahead.
always use ReLU in our dense models? Like, is there no other option for that?
There is other options for that, but in my own projects, I've never used anything other than ReLU so far. That's simply because I feel like I don't really have the knowledge when to apply other activation functions. ReLU, the reason that we use it is it has kind of a calculus background to it, but it solves this problem of neural networks called the vanishing gradient, which is a very, very, very big problem that could occur when you try to use some other types of activation functions. By the way, if you go to Wikipedia and you look up activation functions, there are tons of them, such as hyperbolic tangent, activation functions, Wikipedia. I'll simply show you all the possibilities. There's dozens of possibilities. And we should see some of the words we should start being familiar with, especially the most important, the most common ones. So here, remember, we have our binary step function, right? We talked about that last time, where it can either be 0 or 1, right? We have logistic, which is like it's the sigmoid, right? It's the sigmoid that all of the values are positive. Then you have hyperbolic tangent, where it gets into negative, which I've never used hyperbolic. Actually, I have once. We have rectified linear unit, right? These are the most common ones, right? The logistic or the sigmoid, the step or the rectified linear unit. Then look how many more we have that are simply just they're like achieving the same purpose, but they're not shaped the same way. Here's the sigmoid linear unit, where it like combines a sigmoid and a rectified linear unit. I've just never used these because look how complicated the math is behind it. I simply am not up to this level of math yet. And as a result, neither are you guys. So you don't have to worry too much about it. We'll simply use ReLU inside of it and then either softmax or sigmoid at the end. And that suits a lot of very beginner cases, to be honest. It's very, very good at its job. But now model.summary is working. I don't know why it wasn't working yesterday, but here we have a look at what our model is really looking like, right? 784 neurons in the input, and then it's passing on. We have 784 neurons densely connected to 784 more neurons in the next network, and those 784 neurons in the hidden layer are densely connected to the last 10 layers. And look how many parameters we have. We have 1,200 or 1,238,730 parameters, right? So 700, all of these weights and biases are updated between each layer and the following layer, right? So this is why we let the model do its thing and we don't try to do the weights and biases ourselves or the math ourselves, right? It's going to handle all of this computation for us.
I got an error. It says model is not defined even though I have model equals sequential.
That's weird.
I'll run the cell again.
Yeah, did you put an open close parenthesis?
Okay, now it works.
Oh, you got it? Okay, cool. All right, let's go ahead and convert our data into something that's a little bit more readable for our neural network that we've just defined, right? So let's do xtrain equals xtrain dot reshape. Remember, that's our NumPy reshape function. And do you remember how many images were in the training data set when we were first looking at it on the website?
No.
That's fine. That's kind of irrelevant, actually. We had 60,000 training images and 10,000 testing images. So what we want to do is we want to reshape this into 60,000 times 28 times 28, right? 16,000 by 784, right? So what's going to happen is that it's converting all of our images, which are square data, into simply a 60,000 long array of just 784 pixels that are kind of like stretched out like in a straight line, right? So we have 784 pixels, but originally in the image, they're shaped like a square, right? So what we're doing over here is we're taking that square and we're flattening. Do you remember the dot flatten feature that we used inside of NumPy, where we took like a like a 3x3 array and we flattened it into a 1x9 array, right? Yeah, you can just imagine it like almost like unraveling this 28x28 image into just a 784 long array, if that makes sense. Because we're going to feed in the data not as a square, but simply as a line of pixels, because that's how a neural network takes in data. It takes in flattened data. So, and another thing we have to do is we have to standardize our data. So what that means is we have to divide everything by, I guess, what are the possible pixel values for this grayscale image, right? Or this black and white image. It's on a range from 0 to what? What is the maximum possible pixel value?
250.
255, close.
255.
Colors range from 0 to 255. Very close. But yes, it's from 0 to 255, float 32. And we want to divide this by 255. Oops, 255. So float 32 just adds like it just allows it to get like to be a very long decimal, right? A 32-bit float. Don't worry too much about that. It's just a long decimal. And then the reason that we divide this by 255 is because now what is our new range? So originally we had pixels ranging from 0 to 255. Now what are all of our pixels ranging between? Any ideas? What happens when we divide all of our pixels by 255?
Divide all the pixels by 255?
Yeah, so let's say we had, what?
It makes the image smaller.
It doesn't make the image smaller. It converts all of the pixel values in the same size. Let's actually just take a look at it in action. Let's say we had some pixels, 120, 0, 245, 255, 32, 70, 90, 61, right? So this is just a flattened array of some random pixel values, and they're ranging from 0 to 255, right? So we can imagine that this is a grayscaled image, right? Because it's either black at 0 or it's white at 255, and then everything else is a shade of gray in between, right? So if we were to take this, oh, by the way, don't run this cell, otherwise it'll happen twice. So I'm just going to do this in a new cell. You don't need to copy this down. I'm just going to show you what's going to happen. Don't copy this down. So we have this, right? And if we were to divide this by 255, let's see what happens. Unsupported operand. I'm going to have to use an np.array. Did we import NumPy? I'm not sure.
We didn't.
All right, yeah, let me import it really quick. All right, what happened to our data when I divided it by 255?
Everything was divided by 255.
Yes, of course. But what do you notice about the range now?
It's to 1.
Yeah, awesome. It's only from 0 to 1. So you see how 0 divided by 255 is still 0, but 255 divided by 255 is now 1. So our maximum possible number can now be 1, and everything else is just a number between 0 to 1, right? So this is called standardizing the image by putting it on a range from 0 to 1. So it's pretty easy enough math-wise, right? You simply divide it by 255, and as a result, your only possibilities are from 0 to 1. Hopefully, does this make sense? I hope it's not too confusing.
Wait, so if the only possibilities are 0 to 1, how does this change the model?
Yeah, so basically, remember how we were, it's just basically how the model understands data. It only understands standardized data, and that's between 0 and 1 and all the shades of gray in between. So even for color images, we have to convert all of the color channels into a range from 0 to 1 instead of 0 to 255. Because while we understand 255 as humans, the neural network doesn't understand what the range 0 to 255 means. So we have to standardize the image data by simply dividing it by 255 before we feed it into the model as so. But yeah, we do this, and simply you can just copy and paste this. We have to do this for the testing data as well. So go ahead and replace train with test. And yeah, just do that everywhere. Just copy this, paste, paste.
Wait, should we delete the NumPy?
Yeah, you can delete it. I was just demonstrating what happens to the data.
Oh, okay.
You can keep it actually if you want for reference later. It's up to you if that example helped you understand what was going on. But yeah, here we are standardizing the data, and go ahead and run this cell. And now what we're going to do is one-hot encode our labels. So we'll do train labels equals to categorical y train.
I got an error.
You got an error?
Yeah.
Let's take a look at what happened. Can you send a screenshot?
Or I could just turn on my camera.
Yeah, that works too.
Hmm. Great.
You have a virtual background on, so I can't see it.
International water tasting.
There was a water club at College Park this year. It's very strange.
What?
Yeah.
I heard about that.
Wait, Shreyas, you went to Knox, right?
Yeah.
Apparently Miss Ryan didn't retire and I got her this year.
It should be the text test data. We only have 10,000 images in the testing data set.
Oh, okay.
Replace the 60,000 with the 10,000. And actually, if you think what's going to happen, like you're going to divide the 0 to 1 by 255 again. So you're going to have to run you're going to have to run the cells again, like from the beginning. Does that make sense? Because you already divided it by 255. So if you do it again, it'll divide it by 255 again. So just run all the cells from the top once you fix that. All right, but this line of code, what we're doing is we're basically taking these labels and we are just one-hot encoding them, right? We're one-hot encoding them, Y-train and Y-test. We are just doing that. And let's take a look at train labels and see what the first 5 train labels are inside of train labels. All right, so it looks like this, right? It's one-hot encoded for us. Very, very nice. So can someone tell me what this first image is in the data set?
It's a 6.
Close. Remember,
5.
the data set is from 0 to 9, so you're 1 off.
5.
Yeah, it's a 5. Then similarly, what's the second image in our data set?
0.
Yeah, it's a 0, and so on and so forth, right? So hopefully, I hope this really shows what one-hot encoding means. If anyone still had some confusion about it,
Wait,
but
can you
yeah,
explain like the array again? Like why the first row is like a 0?
yeah, sure. So it's not all zeros. So this is one image from the first set of brackets to the closing brackets. This is one image, and it's been one-hot encoded basically. So this is the label, right? So the original label was a 6. So, but when it's one-hot encoded, it's no longer a 6, right? It's represented as a 0, 0, 0, 0, 0, 1, and 1. This is at index 6,
So
and
it's
then
the index.
yeah, it's the index. It's just putting a 1 at the index for a range from 0 to 9, if that makes sense.
So would that mean the second one is 0?
Yeah, the second one is 0, and go ahead and do the third one as well. What is this third image over here?
The fifth.
Oh, yeah, 0, 1, 2, 3, 4,
Oh,
5.
no.
Yeah,
Yeah.
you're right. Yeah, you're right. Perfect. Yeah. So yeah, okay. I hope that was an aha moment. All right. Last but not least, we need to fit our model before we can look at how we did, right? So we're going to fit on the training data. And I just saw Palash's question on what's the difference between train and test. We pass in the training data, as Sri said, to train the model. And then testing data is to basically look afterwards on how our model did and basically gather an error metric. It's like basically applying it to real world data at the end. Yeah. So let's go ahead and look at train labels. And we will do epochs equals 5. So very quick. Remember, this is 28 by 28 image, so we don't need very many epochs, and it should get pretty accurate. And let's do batch size equals 128.
Wait, so if we did 400 epochs like yesterday, would it overfit?
Probably it would overfit, or it would just, if the model gets it, if the model is good at it, it'll just kind of plateau, and the loss numbers will be kind of the same. But that's good intuition. You can try it and see what happens. Let's run this. It should take a little bit longer than yesterday, and you should see the loading bar now. Hopefully this, yeah, yesterday it happened in like under a second, so you might have not seen the loading bar, but we're literally witnessing the weights and biases being iteratively updated every epoch. We're witnessing the model learning how to detect numbers. This is what is going on right now, right in front of our eyes.
Wait, is the loss like the percent that it's not getting right?
Not quite, but you can think of it like that for now. It's just how many errors it's making. However, it's a very complex way to do it. It uses the weights and biases, and it looks at the previous layers, and then it's a very big process. It's like a 5-step calculus equation where each equation puts itself into the next equation. It took me, yeah, when I was learning it, like I had to watch the lectures about loss like 4 or 5 times before I actually understood what was going on.
For on your screen, you have the loss and the accuracy, but I just have loss.
Oh, you don't have accuracy. Maybe you missed this line up here. In model.compile, did you do metrics equals accuracy? And it should be in brackets.
Yeah, I missed that line too.
Is it just metrics equals accuracy?
Yeah, just metrics equals accuracy. In the future, we can look at that. We can also fill this in with like validation loss and validation accuracy and so on and so forth. But just for this example, we'll do metrics equals accuracy. And I'll run a poll while you guys copy that down and rerun it. And to see if you were able to get your neural network running.
I didn't get it running.
You didn't get it running? All right, let's take a look at what went wrong. Were you able to get the model.fit to work? All right, was it throwing an error?
Yeah,
What was the error saying?
I'll send a picture.
All right. And we got 2 thumbs up from Shri and Palash. Awesome. So that's Shreyas, Arush, and we'll help out Noah.
Your model did significantly better than mine.
What was your accuracy at?
Well, the accuracy is 95%, but the loss was 0.1666.
Even after 5 epochs?
Mm-hmm.
Interesting. So it looks like your initial random weights kind of sucked. You might just want to retrain it or increase the number of epochs. Just train it for like 15 epochs. It won't take very long, and see if you can get a better result.
I haven't opened Discord yet.
All right, I think I put in discussions.
All right. This code looks right. Is that it for the error? Is there a little bit more under it? I can't see the full error.
By a little bit more, yeah.
What does it say at the bottom? Or is it just nonsense?
Value errors, unknown loss function, categorical.
So it should be categorical with a C. Categorical. As such. Spelled as such.
Wait, in which line?
In model.compile earlier on, when we were creating our creating our sequential model.
Wait, can you scroll up and show me one?
Yeah. Right at our like third cell.
Yeah, pictures do take longer to process.
Yeah, they take significantly longer to process because think of what it is, right? Remember, we only had 19 data points being fed in last time, but this time every single pixel is being fed in, which is 28 by 28. When I was doing my science fair projects, my images were 3,000 by 3,000, and that's why they took 32 hours to train because each epoch would take like an hour and a half. So it would just be like, it would just take forever. Did you get that to work, Noah?
I'm running all the cells again.
Okay, was it a typo though?
No.
It was, you didn't spell categorical wrong?
No, it says unknown loss function, categorical cross-sent trophy.
Did you spell it exactly like,
categorical.
Oh.
yeah, did
Wait,
you
it's
spell
up
it
here.
exactly like this?
Wait, it's in the below model summary. Oh, above, yeah.
Yeah, it's above model
Cross-
summary. I can actually paste it in to the Discord, categorical.
Categorical.
Make sure to put the underscore as well.
There we go. My metrics are better now.
Cool, awesome. Yeah, did you just train it for a little bit longer?
Yeah, what is your loss?
My loss was like 0.0 something. Let's check. 0.025.
Yeah, mine was 0.0228.
Yeah, great.
So it's okay.
Yeah, and Polash, like for loss, ideally you want it to approach 0 as time goes on. And that shows that your model is making less and less errors the longer you train. But if you train for too long, we have a fear of overfitting. And overfitting is something, when you watch the lessons back, try to understand when I was explaining overfitting. And if you have questions about it, feel free to just ask me. I would be happy to answer them.
Okay.
Let's see who all has a thumbs up. Shreyas has a thumbs up now, so we're waiting on Noah and Arush. Arush, are you having trouble? I know Noah's working here.
Yeah, it's working.
You got it? Okay. So that just leaves Arush. Are you still there, Arush? All right. He might be AFK. Oh, wait, no. Oh, no, he's typing in the Zoom chat. I don't see anything in the Zoom chat. I'm sorry if I missed your question. My Zoom chat doesn't seem to have a message after 10:22.
He could be typing right now.
Oh yeah, you could be typing right now, or yeah, you could if there's a message that didn't go through, you could paste it in the Discord and I can answer it. But let me know if you got it to work or you didn't get it to work. Oh, yours is working? Okay, very, very cool. All right, let's go ahead and we just have one line of code left. Let's take a look at our final test loss and test accuracy. Yeah, let's take a look. So what we want to do, remember the test set is the unlabeled data and we want to evaluate our model and see whether or not it performed well. We can simply do this doing the model.evaluate function and we call the xtest data and the test labels. And what we want to do is, this is an inbuilt function into sequential models, by the way. It makes it super easy. Remember, this is the training loss and the training accuracy, right? So we should not expect a similar thing with the testing. In fact, it should be probably a little bit lower if our model happened to overfit a tad, right? So let's go ahead and print out test set accuracy. Let's put a colon here and let's just pass in some args. Test acc. And then we want to pass test set loss, right, which measures our error. And ideally it should be kind of close to 0, more or less. And we print in test loss as such. And what it's going to do is it's going to basically, it's not training, but it's actually testing. That's what this little loading bar over here is. It tests on our test set. Does anyone know why this number says 313?
We have 313 images.
Very close, not images. Remember, we have 10,000 images in our test set. How did we?
I'm not sure.
So actually, you can think about it. Yours had 16 loss. That's very high. Well, you can simply let's go ahead and take 313 and let's do. Remember, we had 10,000 images. That's 100,000 divided by 313, and you see how this is 31.9. So it looks like the batch size for our test set was 32, right? 31.9 or 32. So that's how we get that 313 number. Similarly, what was our batch size for training? We actually specified this manually.
128.
Yeah, 128. And how do we get this number 469?
Whatever the total number of like input values divided by the batch size.
Yep, so that's 60,000. Wait, was it 60 or 6,000?
60.
60.
60,000 divided by 128, and there we have 468.75, which is basically like 469, right? So I'm glad you guys remember that. That's how we get this little number over here. It's just the batches. Yeah, try more epochs, Arush, and see if it was better. Otherwise, you might have missed something. That is a very freakishly high loss. All right, but that's it for this example. I hope you guys got it to work. And if we take a look at the accuracy, like, dang, it's 98% accurate at detecting completely like handwritten numbers. So this is something that you could. Have you ever like, I guess in a game or something where you like draw a number and it automatically converts it into text, right? I don't know if you've ever used an app like that, but you might have seen it before.
I think Apple Watch has that functionality.
Yeah. Apple Watch has that even to send texts where you can like draw the letters on your Apple Watch. It takes forever. I've done it before. It takes forever. You have to draw each letter, but yeah, it also has the numbers more specifically.
My set accuracy is 90.8 and my loss is 55.8.
Your loss is 55. That is extremely high. That shouldn't be right.
I'll just run the cell again. I'll see. Nope, I got the exact same thing.
You got the exact same thing.
I think
this
I have the
is
same
2
code
point
as
something.
you.
That's very weird. Why are you guys getting such high losses?
My loss is completely fine. I got 0.0738 million, like a million decimals. More.
Okay. Yeah, what you can do is send me your Colab notebooks after the class, and I can just put a comment about where you might have gone wrong. That way we don't spend a lot of time debugging. It might just be a minor typo because that's usually what leads to such a high loss. But otherwise, it shouldn't be the same as mine, but it should be similar. And it looks like Shreyas had even lower loss than mine. So
Mine was like 0.005 lower than yours.
yeah. So it's again, it's random weights in the beginning, so no one's is the exact same. But yeah, send me the link to your Colab notebooks afterwards, and I'll take a look at them.
What should I call the notebook?
I guess
Like-
MNIST.ipynb. I think that's the best way to name it. I'm just naming it this because I already have like master files, if that makes sense, with the code pre-written up that I'm copying from. But yeah, let's go ahead and hop into the slides now, since we have about an hour left.
Oh wait, what is your? Actually, I'll just ask you for your email after the class.
All right, yeah, I can drop my email in the deep learning chat. I'll just pin it for future reference. If you, whoever has having a wonky loss, just email me or just share your Colab notebook with me on my email, and I will take a look at it. All right, let me close my tabs on this, MNIST. All right, let's hop into computer vision. Computer vision is my favorite topic in deep learning, and I just think image data is truly fascinating. Especially when a computer is detecting things inside of the image without being told what's inside of the image, right? Very, very bizarre concept, and yet so powerful, right? We're making steps in the direction where AI can assist doctors make a clinical judgment, which is just mind-blowing, right? Imagine a computer looking for things inside of an image without knowing what the disease is, right? It just knows that there's a bunch of pixels here, and they're organized in some sort of pattern. And based on those patterns, convolutional neural networks are able to pick up on such insane subtleties inside of the image itself that it can actually help out doctors, and it can actually notice things that even doctors just miss, to be honest. And it's especially helpful in underprivileged areas or areas where there's not that many doctors, right? Because a neural network would be able to go through thousands of images while a doctor might not have the capability to do so in these sort of areas. So steps on the right path, very, very positive technology when used not only in the medical space, but in so many other things. Let's talk a little bit about it. So what is computer vision? So it's the field that enables the computer to see, right? We talked a little bit about this in our final lesson in Python for Research, but we really didn't go into what computer vision was. We were simply going into a little bit of the, I guess, algorithms like erosion, dilation. That's not true computer vision, right? The true computer vision means the model is we're creating some sort of AI that is comprehending what's inside of an image. That's what true computer vision is. This is because in today's day and age, we have an abundance. We have a wealth of visual data that's stored inside of photos and videos at every possible turn of the corner, right? Inside of our pockets, we have cameras. We're carrying around cameras. There's video cameras everywhere that we go, inside of stores, security cameras, public transport, you name it, right? Visual data is being collected everywhere on the factory line, so on and so forth. However, visual data is something that's a task that comes very naturally and very easily to us as humans, right? We can see a dog and instantly know it's a dog, right? From the age of, what is it, like 2 or something as a toddler, right? We can not only describe what's there, but we can also summarize what's going on, right? We can see the man selling hot dogs, or we can see the dog playing fetch, or we can summarize the action that's in front of us in everyday life, right? Walking down the street, you see a dozen things, and that sort of connection is made instantly. It's made in real time. Your eyes as a sensory organ are passing those impulses to your brain, and you're comprehending your surroundings straight away, right? Very easy for humans once you learn how to talk, or even when you're a baby, you're comprehending what's going on around you. You're seeing things going around you, but you might just not be able to describe it. But recognition is still easy, even when you're a baby and you're just learning about the world around you. And we can liken this to an algorithm, a learning algorithm, right? Where a learning algorithm at the beginning, remember I talked about how every learning algorithm starts randomly, right? It sucks. It's kind of like a baby. And it's a baby that's getting older, right? A baby that's getting smarter, a baby that's experiencing more things around it. And as a result, the child is now able to recognize more things and make more informed judgments of the things going on around it, right? So the benefits of computer vision is that we're at a point where we can make rapid and accurate analysis of digital information with the world around us. And by the way, these points that I have on here, these are points that are taken directly from my science fair board. These are some bullet points that I actually had on my trifold poster itself. And I just thought they were interesting to share with you, right? My research is on medical data, yet I always try to introduce it with the broad field of computer vision, right? The broad field of computer vision, and you want to provide some sort of context when you're talking to a judge. I think all of you are going into ASD other than Shri, so I don't know if Shri, you're doing science fair next year, but it's required for everyone else, so that's why I'm bringing it up. But yeah, it's something that you need to provide some sort of context to the field, right? Whether it's the field of computer vision, or maybe you want to provide some context to the field of AI, right? We discussed that yesterday, and how AI is the broad bubble, or 2 days ago, and then we have machine learning inside of it, and then deep learning even inside of that. Yeah, Shri said you'll probably do science fair. Yeah. And try not to use these exact bullet points, right? Because you might be pulling up with 5 other people that have the exact same bullet points as you. So make sure to do some research on computer vision if you happen to do a computer vision project. It's very fascinating, and you should explore how it's in the world around us, right? So oops, is this the same exact slide? Whoops. Yeah, that's the same slide. I'm going to delete this really quick for my slide deck. Yeah, that's the same slide. My bad. But let's move on to the next slide. All right. So current applications of computer vision. If any of you play tennis, or even I think they use it in cricket. I think they use it in baseball. I'm not sure. I don't watch baseball games. But there's a feature called Hawkeye or some sort of replay, right? And they're able to track the exact location of where the ball landed down to a couple millimeters of error, right? And that's a Hawkeye thing, to see if the ball landed on the line, right? Whether it was in or out, in case the human umpire is not able to do so, right? So that's an example of computer vision, very, very popular. It's a multi-million-dollar company or technology of Hawkeye. And then we have self-driving cars, right? Self-driving cars such as Tesla's Autopilot, and now I guess not dozens of companies, but quite a handful of companies that are attempting to tag on their own computer vision data and use things such as object recognition, image segmentation, so on and so forth. You can explore what that is later. And then something that's in the news recently is in Paris and Cannes, and now actually a multitude of other places, they're requiring you to wear a mask inside of public transport. However, they're not going to put a security guard inside of every train car or every bus, right? That's stupid to enforce some sort of rule. Sure, the driver can do it, but like, let's say inside of a subway station, right? There's not like a guy that like checks whether or not you're wearing a mask. And they can't enforce it either. They can't like deny you to access into the training system. So what this company is doing is they're creating a mask detector to see how well people are following it, right? And then they send this data to the public transport, and they're like, maybe you should have a guy standing at this location at this point in time because it seems like there's a heavy influx of people that are not wearing a mask, right? However, can you guys think of some concerns? Why is this not everywhere? Why don't they have this thing everywhere? What are some ethical concerns of computer vision data and taking in security camera footage like this all the time?
Public privacy violation.
Yeah, public privacy violation, right? A big consideration in computer vision. Most people don't want to be recorded, much less analyzed 24/7 by a security camera that's up there, right? And okay, the companies have a promise that they're not storing this information, but it is temporarily stored, regardless of what they're saying. They have to have some sort of temporary storage because it's being fed into a convolutional neural network. So it's not just gone immediately, right? It has to be stored somewhere. So there is a very big privacy concern, ethical concern as to whether this should be everywhere or whether it should not. There are some CNNs that are looking for violence. They're looking for thefts inside of banks, right? Because they can actually respond faster than or just as fast as a human in point in time. And maybe there's not a human inside of that. Shri, I think your mic was unmuted there.
Yeah, I was watching this video.
Oh, okay.
It was a ghast in Minecraft. That's why it sounded so weird.
Oh, okay. That was a really strange noise. I was like, it didn't even sound like a ghast. We just heard like part of it. All right, no problem.
It was like when you see a ghast in the Nether.
Oh, okay. All right, but yeah, hopefully you can see where the ethical concern comes into play. Same with medical data, right? Some people don't want to be analyzed by a computer simply because it's kind of strange and people are not used to it in today's day and age. But I promise you it is going to be something that people are going to have to get used to simply because it's such a powerful technology. All right, now we are actually going to learn about convolutional neural networks from a slide deck that I took directly from Stanford's CS231N course, which is their deep learning course. I deleted all of the slides about like calculus and stuff, and we will actually just learn right from there, which is pretty cool. You guys are learning a sophomore level, college level course, and I think I actually skipped something. I'm gonna go back really quick. So remember how we had loss, right? Remember we had categorical cross entropy loss. So this is loss and cost functions are the same thing, right? Cost is like how much a cost is used in investment. It's like you want to minimize your costs, right? You want to minimize how much you're spending over time. Cost function, aka loss function, it measures how wrong a model is. As a result, it reflects error, and we always want to minimize our loss or our cost. All these further topics, by the way, involve calculus, so I'm explaining what they do, but not how they do it. Then you might be wondering, I guess, how our model makes these, what does it mean to minimize our loss, right? What does it mean to like minimize it, especially when we are in n dimensions, right? We're in multi-dimensional data. Well, we use a process called gradient descent. So gradient descent is the algorithm that's used by loss functions in order to minimize them. This is possibly the most calculus-heavy concept inside of neural networks. Look at this very strange thing over here, right? It's like a 3D, it looks like a topographical map. And gradient descent basically allows us to go from one of these high red points to these low blue points, which means it's minimizing the loss in multiple dimensions, which is very strange. But this is, if you ever are reading about neural networks outside of this class, gradient descent is the name of the algorithm that minimizes our loss function. And then you also remember how I talked about the validation data scolds the model during the training process, right? It scolds the model during the training process, and it uses it to update the weights and the biases throughout the network in order for the model to try again. This process is called backpropagation. So if you remember, I called it a feed-forward neural network where the weights are fed forward into the neural network, one layer after the other, one layer after the other. The weights and biases are going forward. However, there's a process called backpropagation where when the following layer makes some sort of mistake, the backpropagation algorithm, it backpropagates, means it moves in the backwards direction, right? And it slaps the model in the face, and it's like, hey, you suck, you need to fix something. And that's all backpropagation really does. There's a lot of complex calculus involved behind it. It uses gradient descent and the loss function to move backwards through the network, and it just keeps scolding the model until it modifies the weights and the biases to basically achieve the highest accuracy. Or accuracy isn't the best metric, right, in all cases. So just to achieve the best results is a better way to put it, to achieve the lowest loss. That's why loss is a way better metric than accuracy, because loss is not as biased towards unbalanced data sets. All right, that's that. For the rest of the time, we will look at Stanford CS 231 slides. Stanford CNN.
Could you wait a second?
Yeah, sure.
I'm trying to take some notes here and there.
Yeah, go for it. Oops, sorry.
It's fine.
Now's a good time to ask questions, by the way, while Shreyas writes these down, or while you guys write these down, if you have questions about anything. Oops. And let me know when you're good.
Okay. So wait, this back propagation, it goes back into the model. What exactly does it do?
It goes back through the previous layers of the model. So it's like, you know how the model is from left to right, right? But the backpropagation algorithm operates right to left, where I do think the best way to put it is where it's like scolding, or it's like nudging the model that, hey, you suck in the previous layers, fix something in the previous layers in order to make the following layers accurate, right? So it's a left to right, or it's a right to left algorithm that makes the left to right process more accurate, if that makes sense.
Yeah.
It basically tries to minimize the loss function, just like gradient descent and the loss function itself.
So does the back propagation, does it like automatically adjust like the weights and biases?
Yep. Yeah, automatically.
Oh, okay, that's good then.
Yeah. And it's all very calculus based. So remember how I said it's random at first, but then it uses calculus to kind of go in the right direction. I think a way I can probably explain calculus in without calculus is like, let's say we're standing on the top of Mount Everest and we want to get down, right? Let's assume in a perfect world that getting down Mount Everest was a very safe process, right? And no matter what route we take to get down Mount Everest, we would be safe, right? We would be completely fine no matter what route we take. So naturally, what are we going to try to do when we're trying to get down Mount Everest? What would be our goal? If every route if every route is safe, what would we want to do as climbers?
Take the shortest
Find
path.
the fastest route.
Yeah, exactly. We would take the fastest / shortest route. So that is what the machine learning algorithm, or that's what these processes are doing. That's what gradient descent means. Gradient is a 3D slope, by the way. You'll learn about it in multivariable calculus. Gradient is a 3D slope. That's what it kind of means. And what the model is doing is it's trying to find its way to the bottom of the valley as fast as possible. Because what is at the bottom of the valley? Well, it's the minimum of the loss function. So what the model is going to do is it's going to take a couple steps in one direction, and then it's like, oh, this isn't decreasing fast enough. Then it's going to take a couple steps in the next direction, and it's like, okay, maybe this is a little bit faster. Let's keep continuing down this direction, and it's like, okay, the slope is not decreasing that fast over here. Now I'm going to turn a little bit and keep going down. So it's like zigzagging down a mountain, trying to get to the valley as fast as possible. And hence it is minimizing the loss function. I think that's the easiest way to put it without explaining all the calculus and how it minimizes 3D slopes and derivatives and so on and so forth. But yeah, I think you can imagine it like trying to get down a mountain. And I think that's the best way to put it. All right. So are you good, Shreyas, with the notes?
Oh yeah.
All right, great. Let's hop into convolutional neural networks. Yay. All right. Oh, I actually have barely a couple slides, and then we're going to hop into an example of convolution. Let me see. Where's the show view slideshow? There we go. All right, so this is from the 2016 set of lectures. All of these lectures, by the way, are available on YouTube. Stanford posts a lot of their classes online. And so whenever you're working on your own, oh my God, it's flipping by itself. Why? Anytime you want to look back at these, of course you can watch the recordings that I'm sharing with you, but if you want to learn a little bit more about it, and although like the instructor might not be explaining it as simply as I am, if that makes sense, feel free to just Google CS231N, and their lectures are online. I think they have 2017 lectures as well, which are a little bit more updated. And by the way, these researchers that teach this class are very famous. Andrej Karpathy, he's the head of AI for Tesla's Autopilot. And he used to be a lecturer. I think this was the last class he taught before he moved to Tesla. He basically he heads the operations for Tesla's self-driving algorithms using convolutional neural networks and object detection. Very cool. These are the slides that he created, and he was actually teaching this lesson, which is insane to think about. So let's look at how he was teaching it. That's why I picked these slides. They're great. So we saw neural networks, right? We saw all those neurons feeding into the following layer. And now we are seeing something that looks more like an image, right? So here's the letter A, and it's a 32 by 32 input. So we're going to discuss the topic of convolutions. So convolutions is a very, very, I would say, when I was first learning it, it was a very intimidating word, right? Convolution sounds very intense, but we're going to explore what convolutions means, and I think it's not very complicated once you boil down to it. Here's what a convolutional neural network looks like. Now, not are we passing neurons to neurons? Well, we are, but we're actually passing in, you can more imagine it like squares instead of neurons. And these are called feature maps. Feature maps are, we'll see what feature maps look like. They look like absolute gibberish to the human, but they look like very, very significant to a neural network. So what does convolution mean? Convolution is a mathematical operation, and it is simply multiplication and addition. Very simple mathematical operation that a lot of people just neglect when they're like, oh, CNNs, I must just learn the code behind it, and they never understand what convolution really means. It's easy to copy from a tutorial, but it's hard to understand, or it's not even hard to understand, it's just people don't take the time to really learn what this means. So I'm really glad that I'm able to share this with you guys.
Wait, what is convolution again?
Yeah, I'm going to talk about it. It's just a mathematical operation. So let's imagine we have an input, right? This is a 3x3 input, and we can imagine this like, not really like pixels. Let's just say it's an input. It's a 3x3 array of numbers, right? A 3x3 array of numbers, and they're just ranging from 1 to 3, right? Now what we do is we convolve a filter over this input. You can imagine this input, let's actually, for our sake, let's imagine this input as an image, and we convolve a kernel or a filter. So a kernel or a filter is basically like it's a little matrix, right? It's a little 2D array that we pass over an image. So you can imagine it like, let me actually show you what the process of convolution looks like. This is the process of convolution. The green thing is the kernel, and the white thing is the image. So what convolution means is to take this kernel and just keep passing it over one step at a time on top of an image. Does that make sense? So we're dragging this kernel one pixel at a time, and after we go through this, it would actually shift one row down and then do it again. And then it would shift one row down and do it again, and so on and so forth. Such as that. So hopefully this little interactive thing shows what convolution means. Convolution is the process of dragging a filter or convolving a filter over an input. That's what it means. It's like, it's a verb. Convolving is a verb, and it's just the process of dragging a filter over the input. However, the input is the same size as the filter, right? So it's only going to happen once, right? Because the filter fits the entire input. And yeah, so interestingly enough, when we convolve this 3x3 kernel, or this, by the way, those words are interchangeable, kernel and filter for our case, and we convolve it over this 3x3 input, it results in a single output. It results in a single output. So the reason that it results in a single output is because we're doing something called element-wise multiplication. Now, don't be overwhelmed by this word. All it means is that we're going to multiply the 3 times the -1, we're going to multiply the 2 times the 0, the 1 times the 1, and so on and so forth. We're simply multiplying each element in the input by each element in the kernel or the filter. So I guess I'll throw this question up for you guys. What is this middle pixel of the input going to be multiplied by?
0.
0, right?
0.
You're just matching it. You're simply just matching it, and you're multiplying them together. That's what these parentheses are. And then not only do you multiply it together, you just add all of them up together. So you multiply everything together, and then you add the sum, you add the result of the multiplications together, and that gives you a single output. So that's what convolution is doing, is it's boiling down a 3x3 input into just one number. So you can imagine that if we have a 28x28 image, it's going to boil it down. If we were to use a convolutional neural network, it's going to boil it down to something that's much smaller than 28x28, right? Because each of these kernels is reducing or compressing the information into a single value. It's reducing or compressing it into a single value. So let me run a poll to see if does the math make sense behind this first convolution example.
So wait, is every kernel/filter the same?
That's a great question. It's actually, that's the point of a convolutional neural network, is that, you know how the artificial neural network decides on the weights and biases by itself? The convolutional neural network actually creates kernels by itself. And it creates the best kernels that are able to extract very cool features such as curves and edges, and maybe for an animal it would be like a kernel in the shape of their tail or in the shape of their ear or their nose, or so on and so forth. And we're going to look at that in a second. Does the math make sense for convolution?
So wait, so convolution, it's convolving or dragging a kernel slash filter over an input
Yeah,
Yeah.
and the input is an image in our case.
over the input.
Yeah.
What does it do? I'm still confused exactly what does it do when it drags that kernel? Or
Yeah, it just multiplies this pixel with this pixel, right? So the 3 times the -1, it divides the corresponding input pixel with the corresponding kernel pixel, and then it just adds, it does that for every single one. It's called element-wise multiplication, right? Where each element matches with another element, and then it just adds them all up together.
Okay.
Yeah, it's just a mathematical process.
So the numbers in the arrays represent pixels.
Yes, this input, it's just kind of some dummy numbers. I was just trying to make it easy to do the math, but usually these would be pixels in the input.
I
Great
have,
question.
another question. So when
Yeah.
so I understand that you multiply like the corresponding kernel to like the input, but once you like do it for every single square and you get your output, like what does the 2 in the output like square contribute to?
Yeah, that's a great question. We're going to talk about that on the next slide. Does anyone have any other questions before we move on? And I will address that question as to why do we do this? Like, that is the essence of convolution, right? All right, we got a couple thumbs up. I'm not keeping track, so I'll move on. If you have a question, just feel free to interrupt. All right. So let's take a look at 2 very common kernels. So a kernel is, we can have a vertical line detector kernel or a horizontal line detector kernel. Why do you think this is a vertical line detector kernel and this is a horizontal line detector kernel? Take a look at the numbers inside of it.
Because the vertical line detector has 2's like going vertical.
Yeah.
And the horizontal line detector has the 2's going horizontal.
Yeah, and why do we have these -1s on the side? What are we doing when we're convolving? We're multiplying, right? So what does these -1s do? We're
Make
multiplying
the
and then we're
values
adding.
negative.
Yeah, it makes the values negative, or it's basically subtracting away from our final thing. Remember how we multiply everything together and then we add them all up. However, if you add a negative number, right, that's the same as subtracting, right? Simple math. So Palash had a very good answer. So we have the vertical line detector because these 2's in the vertical line are going to give you a very high number. They're going to give you a very high output if there's a vertical line in the image. If there's a vertical line in the image. Is there a vertical line in this image? Does it look like there's a vertical line in this image?
Yes.
Yes.
Yes, right? Because we have 3's lining up on the middle, and then we have lower numbers on either side of it. Sure, we have this 2. What would this 2 be called? That's a very vague question, but what would this 2 be called?
An
Any
outlier,
ideas?
Outlier.
Outlier is a good answer. Something similar.
extraneous solution.
Extraneous solution, also a good answer. When we're working with data, remember there was something that I said people sometimes purposely add to their data set in order to make it fit better to regular data. And I think Shri had looked up the formal definition of it on Google.
It's I literally remember.
It starts with an N.
Noise.
Noise, yeah, noise, right?
Yeah.
So this is a little bit of noise to the left of our vertical line, right? Even when we're trying to draw a vertical line with a pencil, like there's going to be like a little dot or like a little smudge on the side of it, right? So this is a vertical line, more or less, with a little bit of noise on the left, but pretty good overall. And when we convolve this vertical line detector over it, I encourage you to like take a screenshot of this slide and do the math yourself after this lesson. And do the convolution math by yourself, and I've done it for you, and you get it's very easy math. You just multiply all of them together and add them up. You can do it in your calculator in a couple seconds. It yields a 13. Interesting, right? It yields a 13. Very very interesting. That's a pretty high number. However, if we try to pass a horizontal line detector over this, is there a horizontal line in this image?
No.
No, right? We don't have a very clear pattern as to a horizontal line inside of this input, and hence it returns a very low number. It returns a 2. So thinking about how a neural network thinks, what do you think the neural network will be thinking if it tried a vertical line kernel and it tried a horizontal line kernel? What is the neural network? What is going through the computational brain of the neural network? What do you think it's thinking? That, hey, there's a higher number when I pass this type of kernel, and hence what must be in the image if there's a higher number there?
A vertical line.
Vertical
A
line.
vertical line.
Yeah, a vertical line, right? So that is the essence of convolution, is that we pass over different types of kernels. And these kernels, by the way, are constructed entirely by the neural network themselves. So we're not going to tell it to look for vertical or horizontal lines. It's actually very cool. It actually comes up with vertical lines, horizontal lines, diagonal lines. Diagonal lines would look like 2, 2, 2 along the diagonal, right? And -1s everywhere else, or so on and so forth. Usually it's not so perfect. It's usually like -0.5, 0.5, so on and so forth. This is a very good, but yeah, I think this example of convolution really puts it into perspective as what it means, right? We're dragging this convolution over and we're receiving higher values, or you can actually, the way that Andre explained it is that the model actually gets, it gets excited almost, that when it gets a higher number, right, it's more excited that there's some sort of feature there that it should focus on. So this is why the math behind convolutional neural networks works, is because it gets excited when it sees certain features over and over amongst different data sets, right? Let's imagine an example of, let's say we're looking at skyscrapers, right? And we want to classify the difference between skyscrapers and, I don't know, that's a bad example. Let's say we were just trying to make a model that it's a data set, it's a theoretical data set, and it's filled with either straight vertical lines or squiggly lines, right? So the model would automatically probably create a vertical line detector kernel by itself, by the way. We don't tell it anything. We just tell it the size of the input data, and we define the model, and it comes up with a kernel by itself. And then it's also going to come up with some curved kernels, right? Some curved kernels that are able to pick up the squiggly lines inside of the data set itself. So let's think about a real world example, such as a data set that's trying to look between cars and helicopters. What shape is inside of a car that would not be inside of a helicopter? Like a very basic shape. Think about what is a car made up of?
Wheels.
Wheels.
Yeah, wheels is the answer I was looking for. That's a great answer. So what shape would that kernel be?
And a circle.
Circle, right? However, kernels are usually pretty small. So it's probably not going to fit the entire wheel inside of it. Plus, in what?
Like, so would it just like fit a curve? Like
Yeah, it would fit a little. It would fit a little, like almost. You can imagine it like a quarter circle. It would probably be something along the lines of that, right? A little tiny quarter circle. And as a result, right, every image of a car is not the same. Sometimes, if we have an image data set of a car, maybe the picture of the car is taken from the front. We don't even see the wheels, right? So the model would not get excited when it's trying to pass a circular kernel over it. However, if we have images of cars from the side, right, the model would get very, very excited if it passes a little curved kernel. Okay, it's passing it through all of the image. However, when it gets to the wheel, it returns a very, very high number because that little circular segment is matching up with the wheel almost perfectly, and hence it is more certain that this is going to be a car because it's never going to find that curved pattern or a section of curved patterns that are inside of a helicopter, right? Because there are no wheels inside of a helicopter.
How exactly are these kernels determined? Is there like a preset like types of kernels stored within computers, and then when convolution is like initiated, like they test a bunch of those, and whichever one comes with the highest results?
That's a good thought, but no, because every type of image data set, excuse me, is going to have a different type of data, right? Handwritten digits versus dog cat classifier, right? You can't account for everything. When I'm looking for blood vessels, that's completely different than looking for dogs versus cats, right? So no, there are no pre-stored kernels within it. And it all goes back to starting with random weights and biases. It all goes back to the loss function. It goes back to gradient descent and backpropagation, where it starts randomly. It starts with a bunch of random kernels with random numbers in them. And then it slowly gets better and better through the process of training a model, epochs and iterations through the data sets. Then once the model is bad with our validation set, it'll slap the model in face, it'll back propagate, it'll update some weights and biases, it'll look for that easiest path down the mountain, and so on and so forth. And it just does that over and over and over and over again until it finds something it likes. It finds a set of kernels that it gets excited over, sets of features it gets excited over. And that's the essence of a neural network.
So just like weights and biases, with each epoch, with each new epoch, a new and improved kernel is created and tested?
Yes. Well, no, it's actually a modification of the earlier kernel, right? Backpropagation goes back to just the previous layers and it changes the numbers in them. So we define the number of kernels that we want. However, the stuff that's stored inside the kernel is determined by the model initially, and it's updated by the model continuously through training until it gets to the point where it starts making updates and it either gets worse or it stops getting better. Then the model will stop updating that kernel and it'll leave it alone, right? So if we had a data set, yeah.
Our kernels, are they like used to recognize like patterns?
Yeah. It's basically a glorified pattern finder inside of it.
Oh, okay. That
Yeah.
makes some sense.
Yeah. And you can see how this vertical line, it's looking for a vertical line pattern inside of this input image. And when it finds it, it happens so that the convolutional algorithm makes it return a higher number, and hence it gets excited. So the neural network doesn't know what a pattern means, right? However, it does know that greater numbers are, well, they're greater than lesser numbers, right? It knows that higher numbers means it should get more excited. And that's a great way to put it. It's a glorified pattern finder. Good analogy. All right. We have 20 minutes here. Okay, so I guess I can post the question up for the chat. We have 3 possibilities that we can do. So yeah, I'm gonna have to allow you guys to pick, I guess. So we can pick between 3 things. We can either go more into the slides now, or I can actually we can create a custom convolutional operation inside of code, or we can. Yeah, those are the 2 options for today. But if we do the custom convolution thing, that means we're going to only have time for 1 example tomorrow. So we'll pick between the CFAR10 dataset, which is dogs versus cats versus automobiles, or like the cells versus what is it? Malaria detection. Unfortunately, because we are running low on time, I will run. I guess I'll just put something in announcements. You can respond with a thumbs up with which route you want. So go more into slides, do 2 CNN examples tomorrow, go more into slides today, do 2 CNN examples tomorrow, or the second option is to code a custom convolutional operator now, finish slides tomorrow, and do 1 CNN example. Yeah, these are our 2 options.
Which 2 CNN examples would we do tomorrow?
We would do CFAR10, which is a data set. It's a data set that basically, it has everyday objects inside of it, and we're going to create a CNN that differs between like cats, dogs, automobiles, planes. I think there's an example of everything that CNN has to offer in this slideshow. Actually, to be honest, I'm not even sure if we can finish the first option because the code is quite long. Yeah, car, truck, airplane, ship, and then like a bunch of animals. It's a very random data set, but it's like the second step to the MNIST data set because it involves color images.
And wait, what's the other example you would do tomorrow other than this
The
one?
malaria detection.
What if we?
I would do the malaria detection no matter what. I'm
Okay.
going to do that no matter what because I think that's cool. It's either whether or not you want to do the CFAR data set or you want to code a custom convolutional operator right now. It looks like we have more OES for the first option. I kind of take it back because we have a lot of slides, but okay, I'll do my best. We'll boost through it. If you have questions, I don't want to hold people past the time because I keep doing that, and that's my bad. The issue is that I don't have a very good gauge on how long I think these things are going to take to explain. That's why I keep going over time. So my apologies for that. But yeah, let's. It looks like Shreyas has been outvoted. So we will go over this right now. And what I can do is I can send you the code for the custom convolutional operator. I think it's really cool. It's creating a custom vertical line detector and a custom horizontal line detector and passing it over an image to see how it basically shows us what a model is seeing when it does convolutions. It's very strange and very bizarre, but it looks cool. Yeah, we will go on democracy and we will go with option number 1. All right, with the last 15 minutes, I'm going to talk about convolutional layers. So convolutional layers, let's say we have a 32 by 32 by 3 image. Why is this by 3?
RGB.
RGB.
Right?
Yeah, RGB. We are now diving into color channels, 3 color channels. Yay, that makes life a lot more complex, but it also makes it a lot more interesting because most of our data is going to be in RGB format, right? Grayscale images, like we're not in the 1970s or whatever when they had black and white movies. All of our data is in color now. Let's move into the next slide.
That's kind of ironic. The definition of convolution is a thing that is complex and difficult to follow.
Yeah, right. Convoluted, right? You might have heard that word in a book or in just English before. Convoluted means to make something more complex than it needs to be, or to like explain something in a convoluted manner means you did a bad job at explaining it and it didn't make any sense. That's pretty ironic. I hope my definition of convolution for mathematical made sense and it wasn't convoluted. But yeah. All right, so let's go into something that's a little bit less basic than the example that I had previously. So here's a 32 by 32 by 3 image, and we're going to pass a 5 by 5 3 filter or a kernel, and we're going to convolve the filter or slide it over the image by computing dot products. Dot products just means to multiply them together and then add them together. You'll learn about what a dot product is, like, I don't know when you learn about it actually, but yeah, whatever. It just means multiplication and then addition. You know how your math teacher has always told you that the dot also means multiplication in math, right? Well, she lied. It means dot product, except the dot product can take place in 3D, and the multiplication, the reason that it's also multiplication is because you've only worked with one-dimensional stuff in math before. And yeah, the dot product is not the same as multiplication. So you've been lied to your whole life. It was a real weird moment for me when I realized they didn't mean the same thing, but yeah, oh well. You live and you learn. All right, so filters always extend the full depth of the input volume. So that means even though this is a 5 by 5 filter, it still has to have the three color channels in it, right? So these threes have to be the same. They have to match with each other. So if we had a black and white image, it would be 32 by 32 by 1, and a filter would be 5 by 5 by 1, right? So not too complex stuff. And the reason why is because we're not passing a 3-dimensional filter over the image. What we're doing is we're taking the RGB image and we're splitting it into 3 completely separate images. We're separating it into a red image, a green image, and a blue image, and we're passing 3 separate filters over each one of those layers. So it's almost like, how could I put it? It's like, I don't know how to put it. I guess, let's say we had a bunch of Rubik's Cubes, right? Let's say we had 25 Rubik's Cubes and we put them in a 5x5 square on the floor, right? So we have 25 Rubik's Cubes, and you can imagine each one of those Rubik's Cubes as a filter, right? It's still 3 deep, but it's operating on every single one of those individually. So it's like taking one of those Rubik's Cubes and you're sliding it over, or you're convolving it over our entire array of 25 Rubik's Cubes, or our entire array of 5x5 Rubik's Cubes. And that's basically how it's working in 3-dimensional space. And now what we're going to do is we're going to combine convolutions with neurons, right? Even more fun. I hope this isn't getting too complex. But what's happening is that each of these individual dot products is just, the dot product is just calculating a weight and a bias. So you remember how I said all we're doing is multiplying stuff together and then we're adding together at the end? Well, what's that similar to? It's exactly like our neuron model, right? Wx plus b. So the convolution thing is literally just doing weights and biases on pixels. That is all that convolution is doing. It's performing these weight and biases operations on these chunks of the image. So it's basically turning, you know, how we had this, right? It returned a single number, right? It returned a single number, even though our input data was 3x3, right? We had 9 numbers to start out with, and we simply got left with one number. And that one number is y equals wx plus b. That one number is just the result of this multiplying by the weight and adding the bias. So this is, let's see what we have here. Yeah, so when we convolve this around this section of the image, we're simply left with one number. So going back to the example of my Rubik's Cubes, right? If I have 25 Rubik's Cubes in a 5x5 array, and if I were to slide the Rubik's Cube over every spot in the array, and if every spot was one number, what would the size of the array be, I guess, when I'm left over with it? That's hard to visualize, but if anyone followed, is that making sense? What would that be?
Can you repeat yourself?
Yeah, so if I have on the floor, I have 5 Rubik's Cubes by 5 Rubik's Cubes, and it's a whole square. So we have 25 Rubik's Cubes on the floor. And now I take another Rubik's Cube and I convolve it over, right, a 26th Rubik's Cube, and I'm just sliding it over every single location in the image. What am I left with? And if each convolution just returns one number?
A smaller image.
Yeah, you would be left with a smaller image. That's the perfect answer, because
You're
each time,
it,
yeah,
right?
you're just shrinking it because you're just returning one number for every 3x3 Rubik's Cube, right? The Rubik's Cube was 3x3, yet we're only left with one number afterwards, and that one number is what happens by this neuron. So every time we convolve the filter over this image, we're just left with one number. And as a result, our activation map, or the next layer of the convolutional neural network, will be smaller. It'll be smaller. So it is shrinking the image. And when we shrink the image, we're simply left with what's known as an activation map, which is just an array. It's just an array of whatever comes out of wx plus b. It's just an array of numbers as whatever comes out of wx plus b. And not only do we have an activation map on the blue layer, right? We also have an activation map on the red layer and all the other layers. That's really confusing, but yeah, it's RGB, right? It's RGB. However, you can you can pass multiple kernels over the same part of the image. And as a result, you get more than just RGB. You get RGB for a bunch of different kernels. So Shreyas had asked if we have a set of preset kernels that we pass it through. No, but we do specify the number of kernels that we specify. So if we had 6 kernels that were 5x5, we get 6 separate activation maps, right? Because the first convolutional kernel returns a 28 by 28 by 1. Then the second kernel returns another 28 by 28 by 1. However, it's different. and so on and so forth for all of our convolutions. So you can just imagine this like a rectangular prism, or you can imagine this like Legos, and we're just building one layer on top of each other. We're just stacking these activation maps on top of each other. And I think this makes a lot of more sense when we get into the code. Oftentimes understanding the theory behind this, it's just hard to like visualize, I guess, in your head, right? We're working with shapes, we're working with numbers, we're working with math, all in the same. I'm just throwing it all at you, so it is confusing. Yeah, just I guess try not to be overwhelmed and just pay attention to what's going on. All right. So convolutions is just a set, or a convolutional neural network is a sequence of convolutional layers. And all it's doing in between this is it's interspersed with activation functions, right? So you might be asking that, how do we come up with that number in the next layer? Well, we just plot it on something like ReLU or something like sigmoid or so on and so forth. And we simply just perform that operation over and over again. So the structure of our convolutional neural network, we perform convolution, then we perform activation. We perform convolution, then we perform activation. So what's happening to this rectangular prism as we move further to the right? What's happening to it?
It's getting smaller.
It's getting smaller, yes.
What are activation functions?
Activation functions are like ReLU, and sigmoid. Yeah, it's all those, and softmax and so on and so forth. We'll just use ReLU for all our intents and purposes. But yeah, it's getting smaller and it's getting thicker, I guess. Yeah, it's getting thicker. All right. And now if you weren't confused before, this might make it even more confusing, but this is what a neural network sees. How strange, right? Well, what the heck is this, right? It looks really, really strange. It just looks like a bunch of globs. However, this is what a feature means, a feature inside of an image. This is what a neural network sees, right? You can kind of see how these are different shapes, right? The colors look complete, they look like complete gibberish, and don't worry, they look like gibberish to everyone because they are gibberish. They're gibberish to everyone except for the neural network. And that's the whole point of a convolutional neural network. That's the whole point of the black box of deep learning, right? We throw in some input data, and then the neural network does some like black magic with it inside of this box, right? It has a bunch of this gibberish, and then it spits out something that's very strange. The low-level features are like impossible to understand. The mid-level features are also very, very strange. However, in the high-level features, we can kind of see where the model is getting excited. Remember how I talked about the model gets excited on that vertical line example if we have a vertical line? What does these top three things inside of high-level features, what do they look like to you?
Like spirals, kind of.
Yeah, spirals. And inside of an image data set of cars, what is the spiral probably going to match up with?
Wheels.
Yeah, those are
Wheel.
wheels, right? So this is actually, it's very strange, but it's a mathematical representation of a wheel. And this is actually like a 3D image. So it's like a heat map almost. These white areas, it's like you remember my example of a mountain, right? So there's a peak and there's a valley, right? So these white areas are where the model is like more excited, or it's more, that's why it's white. It's because it's gotten excited at those areas, and that it looks like a wheel, right? So if we were to pass this kernel over this image, man, would it get really excited when it passes over the wheels. When it performs convolution over those wheels, it would return a really, really high number. And as a result, it would be pretty sure that this is a car, because cars have wheels that are shaped like that, while other things do not. So it's gibberish at the low level. It's still pretty much gibberish at the mid level. And then we start seeing what the model is seeing kind of at the high level. Some of these are still just absolute gibberish to me, to be honest. Like, what is this honeycomb looking thing? Like, I don't know. Maybe it's like the grill of like the car. I don't know. I've never seen a car with a honeycomb grill, but it just looks very strange. And some of these shapes are just completely foreign to me, and they're foreign to everyone. But yeah, that's what's going on.
Could be like the window, possibly. I don't know.
Yeah, it could be. Yeah, some of these could be the windows. It could be more features of the wheel, the headlights, right?
The
Um,
honeycomb could be like the design on the wheel.
Yeah, it could be a multitude of things. But remember, these features, these are kernels that should be able to generalize very well to the data set, right? So it would be pretty stupid to have, like, let's say we had a car with a honeycomb grill. How many cars have you seen with a honeycomb grill in the front, right? Very few. So there would probably not be a honeycomb feature or a honeycomb kernel if a bunch of those cars did not have it, right? Because the model is trying to do the best on a generic set of data. So it probably won't try to deal with specific use cases. Because even with the honeycomb grill, it could probably still pick up the wheels of the grill of the car with a honeycomb grill, right? And still be correct, right? Even without having a kernel that gets excited when it passes over that very specific shape. All right. Let's look at ignore the math, by the way. It's redundant for you. I just couldn't delete this because I still wanted to use the left side of the slide. And this is going to be, yeah, okay, 2 more slides and we're going to stop. This slide and the next slide. So this is one filter leads to one activation map, right? What we're going to do is we're going to try, so at the top here, all these blurry things, these are kernels, these are filters, these are 5x5 filters, and we have 32 of them. I'm losing my voice. I'm going to grab water. I'm sorry, I'll be right back. So that I'm not like not saying anything. 1 second. All right, I'm back. I feel like I've been talking for like the past like 5 weeks, just like every day. So I lose my voice very frequently. But yeah, let's take a look at these filters again. We have 32 of these filters. Remember how I talked about vertical lines, horizontal lines, and so on and so forth. However, our neural network usually picks up on kernels that are more specific than that. So if you look at this image of a headlight, we're going to pass over a kernel and take a look at where it gets excited and where it gets non-excited. This is what the computer sees when you pass a filter over a section of an image. So can you kind of see how this blue one over here, it looks kind of like the headlight, right? It got pretty excited when we passed this orange feature over the headlight, and as a result, it took better shape than some of the other ones, right? Some of these look like gibberish. However, this blue one looks pretty much like a headlight. Does it not? Do you guys see how it looks like a headlight? At least the shape of it, right? Yeah, it does look like a headlight. Or is that the tail light, I guess? I don't know. This is like a square car. But
Car light,
what?
like
I
just
think
a light
it's
from a car.
I
Yeah,
think it's the back right.
Same. Wait.
I think it's the back right as well. Is that called the tail light? I don't know.
Yeah.
Wait. What about the photo from the bottom left? The second from the bottom left.
Second from the bottom left, this one over here.
Yeah.
Yeah, that's also probably a pretty good one, and this should match up with some of our filters here. So the reason that let's take a look at the blue one first. The reason that this one looks more like a headlight than the majority of the other one is because look at the kernel that was passed over it. Does this not look like an orange separated by like kind of a line, right? It's extremely blurry, but that's because it's a 5x5 filter. It's literally 5 pixels by 5 filters. So, or 5
It looks like it could
5
be
pixels.
it looks like it could be like a blue car with a red tail light.
Yeah, exactly, right? But and then if this was operating on all of the color channels separately, it would, regardless of the color, it would be able to pick up on this pattern, right? Some sort of orange feature separated by some sort of background with it. So that's why this kernel, this very specific kernel, yields a much better activation map. All these gray images are called activation maps. And it's what's fed into the following layer of our convolutional neural network. So that's why it yields a much more accurate looking activation map than some of these other gibberish filters on the top, right? Or at least to our eye, they look like gibberish.
What are the dimensions of each kernel slash filter, are they always the same? Like, are they always 5 pixels by 5 pixels or 5 numbers by 5 numbers?
That's a good thing. When we're coding it, we usually try to stick to small odd numbers. So 3 by 3 and 5 by 5 are a very safe bet. So when we create our own custom convolutional neural networks, we're going to use 3 by 3 and 5 by 5. It's a pretty safe number to work with. Small odd numbers are what we work with. And the reason behind that is, I will talk about that in the beginning of the slides tomorrow. But great question. Yes, 5 by 5 is a good number. The smaller the filter, the better it is to pick up on subtleties, right? Because that means you can have a lot more like nuanced, like little sections of the image that you're analyzing. However, it's going to take longer to train, right? Because a 3 by 3 filter has to go through a lot more convolutions than a 5 by 5 filter, right? Does that make sense?
Yes.
Because a 5 by 5 filter can like cover more ground. It's like a runner that has longer legs. They can cover more ground in the same stride.
So the smaller odd number filters, the reason why they're used is because they can pick up more subtleties.
Yeah, but there's like a reason that you use like 3 by 3 instead of 4 by 4, and I'll talk about that next time. Like you don't use even numbers that much. Or I've really never seen even numbers. But yeah, okay, so what a convolutional neural network looks like is that it's a convolutional layer, and then it passes into an activation function. You see how the activation function basically thresholds it. You remember how we thresholded images in lesson 8 of PFR? It's similar. That's what the activation function is kind of doing. It's thresholding the image. And then we just do that process over and over again. And then the last layer is our fully connected layer. What's another layer what's another name for fully connected layer? Think back to all the examples we've done.
Is it
Fully
a dense
connected.
layer?
Yeah, it's the dense layer, right? So fully connected means every layer of this red pooling layer is connected to the fully connected layer, which is a dense layer. And this dense layer is going to be 1, 2, 3, 4, 5. It's going to be 5 neurons. It's actually 10 neurons, but Andre just like cut off this on the slides, right? There were 5 other classes that were just too insignificant to list. And we'll talk about what pooling layers are next time. It's essential to a convolutional neural network. But here we have it. That's the essence of a convolutional neural network. We'll talk about pooling next time, and then we will do 2 CNN examples tomorrow. If we do 2 examples tomorrow, I don't know who's available to stay around, but it might take me like half an hour over time, unfortunately, unless you guys want to skip the first CNN example and just do slides and the malaria detection. It's up to you.
I should
But
be able to stay.
you can stay? Okay, cool.
Yeah, I can stay as well.
You can stay as well? Okay, awesome. Then we can do 2 of the examples. Anyone else? If you're not,
I should be able to stay.
you can stay? All right. Let's say that we're going to go from 10 to 12:30 tomorrow. What about you, Arush and Noah? If that's a no, that's fine, by the
Yeah,
way.
I
Then
can
what
probably
we can,
say a little bit more, yeah.
okay, and if you can't stay, by the way, we can do like your example first so that like the people who can stay will do that example second. So if anyone has to leave early, like do you want to do the CFAR data set, which is like, this is the CFAR data set, cars, trucks, airplanes, or do you want to do malaria data set? It's up to you, entirely up to you. And we can do that one first so that if you do miss an example, you'll miss the one that you like weren't as interested in, I guess. But yeah, you can let me know. You can just DM me after the class if you do have to leave early. But otherwise, I will go with the time frame from 10 to 12:30 tomorrow. And yeah, it should be a really good lesson since we're hopping into the code behind CNNs. I hope
Wait,
this is starting.
for tomorrow, correct?
Yes, this is for tomorrow. We're done for today. I'm going to stop here.
Oh, okay.
But yeah, I hope you're starting to understand what convolution means and how the model is starting to kind of make these mathematical predictions. I'm going to stick around for probably another 10 minutes. I really invite you to ask questions since we're barely over time now. So if you want to ask questions, I'm here. Yeah, but otherwise I will see you guys tomorrow. And I'm looking forward to coding some of the CNN examples to close out our little, what is this, like extension rapid fire introductory course. But yeah.
Can you proofread my MNIST